Welcome to our Team 43's presentation of our solution to the Chandrayaan Moon Mapping Challenge. Our objectives in this challenge were, firstly, to develop an ML model to upscale lunar terrain images, and secondly, to create a global high-resolution lunar atlas using the model upscaled images. The first step was to analyze the data provided to us and prepare it for use in the objectives. We generated training data for the ML model and collated information from images for use in making the atlas. Three data sources were available to us: images from the terrain mapping camera and the optical high resolution camera of the Chandrayaan 2 lunar orbiter, and narrow angle camera images from NASA's Lunar Reconnaissance Orbiter. We faced a few challenges when pursuing our goals. It was difficult to download and store TMC image files because of their large sizes and slow download speeds, and to handle images of such large sizes. We scraped information for all TMC files from the Pradhan website using browser automation software. We also extracted data from the shape files using QGIS. We decided to focus on a smaller region of the moon with a high density of TMC images as shown. QGIS was used to create this display of auto-rectified TMC images. Roughly, the region we selected, as mentioned in the previous slide, has been shown. As you can see, only a few OHRC images overlap with the TMC images. We did not think this would provide sufficient data, so we decided to use NAC images. These are various details why we chose NAC images over OHRC images. Regarding resolution, we felt that the OHRC images had too high a resolution for the model to be effectively trained on them. NAC images almost exactly fit the resolution we were trying to upscale to. Our process involved, firstly, finding NAC images that were completely contained within a TMC image, calibrating the NAC image using ISIS, the US Geological Survey software for handling such images, and then cropping the TMC image to the coordinates of the NAC image. We then matched the contrast and brightness of the cropped image to the corresponding area in the browse image, and the same with the NAC image. Then we finally rotated the cropped AMC image so that the position of features, such as craters, in both images matched. Finally, we cut up the images into small squares, as shown. The ML model was then trained on this data.
The process of getting a high resolution image from a low resolution one is termed as super resolution. We use two models for super resolution, namely SRGAN, an architecture based on generative adversarial networks, and SwinIR, based on Swin transformers. These images summarize the model architecture. Above is the generator part, which actually generates the upsampled images, and the other one is the discriminator, which classifies between a fake generated image and the ground truth. The loss terms alongside show the generator loss and the discriminator loss. The discriminator loss here is also known as VGG loss. The equation on the top shows the overall model loss. In the process of developing an AIML model, we started by creating a model from scratch. The advantages of doing this were the model was lightweight and we are not constrained to some limitations of training data, and model could be directly trained on grayscale images. So the question is, why did we shift to pre-trained model? It had many advantages like huge and diverse data set, and those data set were trained on large number of epochs. On a small data set like of ours, we will face some disadvantages like overfitting on training data. We might undertrain the model due to limitations in time and resources, and we cannot outperform the results shown by the pre-trained models. Hence, we shifted our focus to pre-trained models. The pre-trained model is trained on 35 lakh ImageNet datasets. Further, we trained it by two types of datasets. First, 1000 lakh images and the 4 times downscaled version. Second, 13,000 lakh images as ground truth and the corresponding TMC2 images on the same lunar coordinates as input. On comparing the results, the second one gave better results and we further moved on with it. These images show the loss and evaluation metric values while running the epochs. While this shows the generator and discriminator loss graph. These two are the average SSIM and SAM values on validation set. We faced some challenges while transfer learning pre-trained models on our custom dataset. First, the model was pre-trained for 3 channels and exactly 4 times upsampling. Second, how to generate images comparable to the resolution of that of OHRC. The solution that we came up with were, we modified the images to 3 channels, created dataset that was nearly 4 times downscaled to the ground truth, and created a cascading pipeline to generate near to OHRC resolution images. This image shows the flow of our cascading pipeline. The input image was 240 cross 240 in dimension. Then we cropped it and feed it to the model to give a 4 times upscale 96 cross 96. Again merged it to 960 cross 960. We repeated this process again. So finally, from input of 240 cross 240, we got an output of 3840 cross 3840. These were stitched to create a 1 degree cross 1 degree stitched moon atlas of high resolution images.
The next the next approach involves using the SwinIR architecture for constructing the high quality image. As you can see in the diagram, there are two modules implemented, one for extracting shallow features and one for extracting high dimensional features. The shallow feature extraction is deployed using a 3x3 convolution layer. The deep feature extraction module is handled by residual Swin transformer blocks. Each residual Swin transformer block consists of Swin transformer layers followed by a convolution layer. The shallow features and the deep features are residually connected and feeded into a subpixel convolution layer which upscales the image to the required high dimensional output. This predicted output and the ground truth value uh, are measured using the loss function of an L1 norm. Now I would like to explain the Swin transformer layer. The Swin transformer architecture consists of using shifted windows between two successive transformer layers. As you can see in the diagram, the Swin transformer layer consists of two layer norm layers, one MLP layer and a multi self attention mechanism layer. We initially the model breaks the images into patches, and these patches serve as pixel features for the linear embedding layer and are passed through the embedding layer to get the output dimension of C. The patch merging architecture of stage 2 groups the 2x2 neighbor patches of the image and applies a linear layer on the 4C dimensional concatenated features and outputs a dimension of 2C. Now I would be focusing on the training and challenges of done during the SwinIR architecture. Due to the reason similar to the SREAN model, the pre-trained weights which were used had superiority in terms of performance, and it reduced our training time considerably since we did not have exact corresponding NAC to TMC images as labels. We bicubically downsampled the image 4 times to generate the training data. For achieving a 16x scale from the TMC to images, we executed the forward pass twice from the generator and used a cascading loop similar to the SREAN model.
For the second part of the problem statement, that is the lunar atlas solution, we had a three-step approach, namely image processing, tile segmentation, followed by atlas creation. Initially, we were greeted with more than 8,000 TMC images. After reading the documentation, we started working on the orthogonally corrected images, that is the ones having OTH in their file name. The files were then downloaded from the Pradhan portal, and the vertex coordinates of the files were scraped and stored in the spreadsheet. Using PDF4 Viewer, we were able to visualize the file, but only one at a time. We then proceeded to construct an algorithm that was able to convert every TMC TIFF file into a TIFF file with the data type of unsigned 16-bit integer for easier processing. Next up, we created 16,200 blank TIFF files having a resolution of 5,000 pixels per 2 degrees of the lunar surface. Now only the TIFF files without vertex coordinate disparity were chosen. That is, only those files that had their correct coordinates in the form as shown in the figure were chosen. These files were then rescaled to match the resolution of the tiles and then separated into chunks such that each chunk was able to completely fit inside one of the 2x2 degree tiles based on the coordinates of the chunk border. These chunks were then mapped onto their corresponding tile and each pixel value was calculated. This was done by taking mean if pixel value was non-zero in both the tile and the chunk, or the higher value if 0 was present in either the chunk or the tile. Once we had processed all the TMC files and obtained the tiles, it was time to piece them together. For lunar atlas generation, we created a large matrix and, much like a jigsaw puzzle, filled in the resized tiles according to their vertex coordinates. The final atlas with the size of 1.1 gigabytes was then saved, which can be majestically seen on this slide. While constructing the lunar atlas, we were faced with a lot of challenges and made some critical decisions along the way. MATLAB was used because of its high speed of processing images due to out-of-the-box multi-threaded matrix operational capabilities. The tile size was chosen to be 2 degreed because it led to a great trade-off between file size and retaining the original image quality. The atlas size of 1.1 GB was also a result of the MATLAB constraints. In order to handle large images, some of them which even went as high as 50 gigabytes, we paged 200 GBs of NFSD. Here we have listed the references we have used while approaching the problem statement. Thank you.